It worked. Yay. Okay. So we're going to go over 24. I think the plan is I'd like to go over 24, 25, and maybe 28 if there's time. 28 is the dreaded. It's a ramp and an Atwood machine. The two worst things in the universe, right, Julia? There's one, yeah, the 25 is going to be a spring. That one's not so bad, really.
Spring on the Atwood machine.
Oh, what you got to have is the ramp with friction and a spring and an Atwood machine. And then that whole thing is just part of a bigger Atwood machine. That's the real test of greatness. So 20, oh, it's the sun. Look. Yay, the sun is out.
It's all right.
That snow yesterday was like the perfect consistency too. It was nice. Okay, guys, so on 24, there's a ramp and there's friction. Okay, so maybe I'll draw it like this. There is friction between the ramp and the block, and obviously also between Bob's feet and the ramp, or else he'd slide on the ramp. 100 kilogram block. Okay, this is a 20-degree incline. So the first thing we want to ask ourselves is, do we understand the premise of the problem, which is that Bob is pushing this block upward. So Bob is going to exert some force. Here's the force from Bob on the block. Okay. Now Bob is fighting how many things? What's he working against?
Gravity and friction.
He's working against gravity and friction. Okay. So there's two vectors pointing down the ramp, right?
Yeah.
So these vectors pointing down the ramp, the force, let's say force from gravity parallel to the ramp, like kind of like, okay, would be mg sine of theta. And then there's the force from friction. Now, here's the thing. At first, it's asking how much force does Bob need to exert on the block to get it moving? So to answer that question, do you want to think about static friction or kinetic friction? Static. Because the question is, how much force does he need to get it moving? Does that make sense? Part B is asking how much force does he need to keep it moving? So the question of how much force does he need to break that static threshold, does that make sense? Because it says he's initially at rest. The problem says initially at rest. So the first thing is going to be static friction. And that'll be anything, that'll go all the way up to, but not exceeding, mu static times mg cosine theta. Hopefully that's, I'm writing a little small for some reason. I don't know why. Out of my control, right, guys? Anyway, does that make sense? So at that critical moment when he breaks the static friction, when he exceeds this value, the equation would be mg sine of theta plus mu static mg cosine theta would have to be equal to the force that Bob. Do we feel okay about that setup? Mm-hmm. Now we just have to plug in the values. So this would be 100 times 9.8 times sine of 20. U sub s is 0.4 for the static case. And we would then just solve, okay? So this was to get it moving. To get it moving. How about to keep it moving? Is anything drastically changing in the situation? Anything like super big? No. Like the force diagram's gonna look pretty much the same, but one value will actually, well, I mean technically it's two values, but what thing will change once a thing starts moving? Which of these things changes?
The friction.
The friction. So once he starts moving, it's now going to be kinetic friction. So it's going to be the same formula pretty much. But instead of mu sub s, mu sub k. So does Bob require less force or more force? Less. And again, this is something that I think we may have all experienced at some point, which is you got to get it moving, takes a bit more force, but then once it's moving, you can kind of let up on the force a bit to keep it at that rate, to keep it going. By the way, does it make sense why moving at constant speed, what's the net force if you're moving at constant speed? Zero. Net force constant speed means no acceleration, which means there's no net force. So it means these are balanced. That's why, again, it's an equation. Okay. I guess you feel okay about that?
Yes.
Let's look at a spring. Spring. Okay, this is a 10 kilogram block. Before we analyze this question, it's involving a spring, so we always ask kind of the same questions when your spring's involved. How much is the spring stretch, or what's the spring constant? Will a question like this depend, excuse me, on this number 10? Will the mass of the block matter? Maybe let's rewind a second. Does the mass of the block matter for this problem? Because we're asking the question, how much force does Bob have to exert? Well, put yourself in Bob's shoes. If it's a 100 kilogram block, that's a lot harder to push than a 20 kilogram block, right? Let's say there's some spring here. Will it matter how heavy the block is if we want to ask about like how much does the spring stretch? Yeah, it's going to matter. So don't forget to use, it doesn't have to be all mathematics, right? We can always throw in some just basic reasoning. Okay, so it's a 30-degree incline. What?
It kind of felt like a trick question, so no, it doesn't matter. At first I was like, well, the max is going to change no. But then everybody was silent. And I was like, well, shoot.
That's the classic, there's certain kind of questions that physics students will get wrong more often than like a common person. Like that would be a good example of one where I'm going to put a block on this spring. Will the heaviness of the block affect how much the spring goes? And physics students get kind of like conditioned to go, oh yeah, it's invariant. The mass doesn't matter. But if you're not looking at it through the lens of, say, a physics course, it seems pretty obvious. Now, granted, there's a lot of questions that if you study physics, you're going to get that correct over a person who hasn't studied it. But anyway. So I'm just reminding you to. That reminds me. I'll show it to you tomorrow. This little ramp thing. I think it's a great example of that kind of question. This little ramp I've got over here. I'll have to find marbles for it, but we'll raise a pair of marbles down that and make a prediction.
I have a lot of hobbies.
Hot Wheels track. Yeah. We will do a famous physics problem where it's like you got a Hot Wheels car and you got to send it around the loop-de-loop. And how high does the ramp have to be theoretically in order to make it around the loop?
Well, let's just break possible. That would be cool.
True. Or you can ask, if you know the height of the ramp, how much G-force is there on the guy in the car as it comes around the loop-to-loop? That's another fun one. And yes, the higher the thing, the you can crush his bones, you know, with the centrifugal force. Okay, so this says that 10 kilogram block, and what happens to the length of the spring? It was originally at 70 centimeters, and it changed to 90 centimeters. And so what's my change in length? 0.2 meters, right? Is everyone all cool with that? Okay, so now the question is, and of course the spring constant is how much extra force was there on the spring divided by how much length did the spring change by. How will we get this number here? Because we're solving for this. What? Yes. Force of gravity.
Okay, yeah.
Force of gravity. Those are two good answers. So it's how much gravitational force did we kind of add to the system by putting the block there, and the quantity of that. So this vector would be mg sine theta. And so we just need to throw in 30 degrees. We need to throw in 9.8. We need to throw in the mass, which was 10 kilograms. And so there you go. We'll get our spring constant. And then on 26 and 27, they're very similar questions. It's just going to be you kind of set up the same exact. You set it up the exact same way, but on 26 you're solving for the new length of the spring. 27 you're solving for what would the theta value be in order to double the length of the spring. Okay. So, let's squeeze one last thing in here, and then there no video tomorrow because tomorrow's a work day. You'll hopefully be able to proceed with this stuff somewhat efficiently. All right, the dreaded Atwood machine. The dreaded. It's not that dreaded, right? Not PBA. All right, there's a 30-degree ramp with a 60 kilogram block connected to a 40 kilogram block. There's no friction, frictionless ramp, frictionless pulley. And we're going to answer the same question we always answer when it's an Atwood machine. What's the acceleration of the system, and what's the tension in the rope? Now here's the nice part. Is this question going to be fundamentally different than like the old Atwood machine? No, it's the exact same thing. This is the beauty of physics. The way we learn physics is in this way that once you have this idea of like setting up an equation, setting up F net equals ma with a force diagram, you can apply that to like a million different things. So even though we've changed the nature of the system, it's going to be still analyzed the same way. So all you got to do is go, how much force pulls down on this dude? Mg, so 392 newtons, right? And then how much force pulls him up?
Whatever the
To tension, which we don't know that value yet, right? We don't know how much tension is in the rope, so we just call it T for now. How about this guy? How much force pulls him down the ramp? Very good. So mg sine theta. Mg sine theta. Let's get a number for that.
294.
Thank you. All right, so right now, let's pause. No, well, first, put the little t in there so that our diagram is nice and readable, so the person reading our work sees, okay, We know, we can see what's going on here. It's the same t-value, but which direction is this thing gonna go? That way. Which might not have been, I mean, I don't think it's obvious at all, because I mean, 60 is bigger than 40, but because of the ramp, it ends up only having 294 newtons down the ramp, so this beats that. So my formula, I'm gonna write F net. All right, give me 2 seconds here. Write this formula for each block. So I'm gonna go 392 minus T equals MA, and then for this block, it's T minus 294 equals MA. We've solved those a bunch of times to use elimination. All right. And then once you get the acceleration, plug it back in to solve for the tension. Yay. End stream.